Okay, so thank you very much, Professor Hacht, for your introduction. And good evening, everyone, and good afternoon. So it's lovely to see you on FreeFEM days this year.
Yeah, but for you it's evening, so.
Yeah, yes, already evening in Japan. Um, my name is Li Hao, and I'm studying in Kyoto University under supervision of Professor Nishiwaki and my co-advisor, Professor Yamada. And we are working with PL for doing the parallel computing using FreeFEM, PETSI, and MNG. So today's topic, we are going to talk about our latest progress on the structural topology optimization using FreeFEM, PETSI, and MNG. Okay, so here is the outline of today's presentation. First, I would briefly introduce the latest application of the structural TO technique in the industry. And then we overview our level set topology optimization methods based on the reaction diffusion equation. Next, we show several nice features of the body-fitted adaptive mesh technique integrated in our framework. And after that, we quickly discuss the numerical implementation using FreeFEM, PETSI, and MNG. Finally, we show several classical benchmark optimization testing case. Okay. So before we start the introduction part, I would like to show you several interesting designs, and we prepare a short video to all of you. Okay, so the first example is to optimize the aeroplane bracket structure. Okay, so this is the optimal solution. Second one is architecture design. So we have a letter A in the middle as a fixed design domain. And we are optimize the supporting structure of the roof. In this example, we are all optimizing the channel layout to minimizing the power dissipation of the fluid flow system. So we can see the flow velocity distribution before and after the structure to be optimized. And here we show a multi-physics testing example, the fluid structure interaction problem. So this is the 2D and 3D infill structure design. And this is a so-called wet FSI problem. I will explain the details later. And we can see the mesh evolution iterative history here using the body-fitted adaptive mesh technique. And this case is extension to 3D for design solar plate support. So here I'd like to introduce the basic concept of the structural topology optimization. So structural optimization method has been developed for several decades, and it can be classified into three major categories: size, shape, and topology optimization. So the TO techniques is actually the youngest one among the three, and it is a mathematical method that optimizes the material layout within a given design space for a given set of loads, boundary conditions, and constraints, with the goal of maximizing the functional performance of the system. So with the TO technique, we can get any shape with the design within the design space instead of dealing with the predefined configurations. Okay. So here we can see several industry applications. First one is the architecture design. So this is the Qatar National Convention Center. So they are using the BISO technique to design the roof supporting structures. And people can also find an efficient cooling channel layout by solving the thermal fluid optimization problem. Okay. Also, very recently, the scientists from the medical science field are trying to use the additive manufacturing coupling with the TO method to customize the patient-specific reconstruction implants like this. And of course, we can find many other applications such as the compliance mechanism design and the aircraft wing design and etc. So next, I want to share some latest trends in the high-resolution 3D topology optimization. The early large-scale topology optimization was mainly discovered in the density-based method. So the figure on the top left corner shows an aircraft wing design by Professor Auger in 2017. So they're using a PETC and a fully distributed framework to design this structure. They solve over billions of DOF on a cluster with over 8,000 processes. And besides the density method, in the recent year, the level set based method is adopted to solve the large scale computation, because the level set based method is famous for its strong ability to track the clear boundary. So we can transform what we see to what we get. And these pictures is cited from Dr. Fepon in his very recent work. So he did very pioneering work to couple the body-fitted adaptive mesh technique in the level set method, and already report several 3D design last year in the FreeFEM days. But here we wanted to mention that their method is using the Hamilton-Jacobi equation for updating the level set field. And we must set many holes for the predefined structures, and shape will variate based on the shape derivative, means that the new holes cannot be generated during the iterations. So to overcome such a problem, here we'd like to introduce our level set method based on the reaction diffusion equation. The idea is that to represent the presence or absence of the material in the design domain over time, using the sign of the level set function, we assume that the variations of the level set function are proportional to the topological sensitivity if prime here. And once the level set field is obtained, we map the level set to a characteristic function chi. And then we can use the chi to interpolate the material properties. For instance, in the Lamé system, we interpolate the elasticity tensor C. In the Laplacian equation, we interpolate the thermal conductivity kappa. And in the fluid mechanics, we can interpolate the inverse permeability alpha. So basically, our method is a kind of so-called ersatz material method. Okay. And with this assumption, we can mathematically prove that the variation of the Lagrangian, always say the sensitivity with respect to the characteristic function chi, is decreased with the time evolution. Okay. But the optimization problem described by the reaction equation is an ill-posed problem. So it should be regularized by a diffusive term here. And eventually, we use the reaction diffusion equation to update the level set function. And this method was firstly proposed by Professor Yamada. So since we use the topological sensitivity to update the shape, so in our method, the new holes can be generated, combined, removed, and deformed freely during the iterations. So from this figure, we start from different initial shape, but finally we can get a practically identical solution. And then we test this benchmark problem, this cantilever benchmark, using different mesh resolution. So a nice feature is that in our method, we can somehow restrain the dependency of the mesh resolution to the optimal solution. And also we can control the complexity of the optimal structure by tuning the regularization parameter tau. Okay, let's see how we integrated the body-fitted adaptive mesh technique in our method. So here, step one, we solved the RDE, reaction diffusion equation, which is semi-discretized in time. Then we get a new level set field. And step two, we sparse the mesh file and store the mesh. Step three, we roughly discretize the newly updated omega into the old mesh T based on the zero level set interface. So if the zero level sets cuts the old mesh, we have added some new nodes on the boundary. That is why we called it a body-fitted adaptive mesh strategy. And finally, we improved the local mesh quality for outputting a new mesh using step 4. And to implement this algorithm, we can use the MMG platform. So with MMG, we can set the maximum and minimum edge size of the global computational domain. And we can also impose the local edge size along the zero level set interface. So with these two features, we can get a very high resolution boundary, but at the same time remain the coarse mesh at the far field. And another feature is that when solving the multi-physics problem, like the fluid structure interaction problem, we can easily extract the computational domain for solving the Navier-Stokes and for solving the elasticity on this blue domain. Another interesting observation is that when we are going to doing some post-processing for generative design, for example, in this traditional fixed mesh topology optimization framework, we can see a quite smoothing procedures in between the generative design and the output CAD. But using the body-fitted adaptive mesh, we can preserve much more design details when we output the CAD data. So this is very important, especially in the fluid optimization. Okay, so next is the numerical implementation. Here we just quickly go through the parallel computing strategy since PL has already discussed this morning, and he will give an in-depth talk in the tutorial session. So in our framework, after decomposing the mesh using the partitioner like the Matisse, the distributed assembly of the weak forms of the PDEs is performed by the FreeFEM. And after that, the discretized linear system are passed over to the PETSI. They are solved using the multi-grid preconditioners. For example, we use the GAMG for solving elasticity and HyPre for solving the reaction diffusion equations. And for solving the large-scale nonlinear problem, such as Navier-Stokes, we are using the augmented Lagrangian preconditioner, which is proposed by Dr. Mullin in 2019. And this preconditioner is scalable to the problem size up to 75 million unknowns on a supercomputer, which has 2,000 processes. And also it is an open source preconditioner to the users. Okay, so here we quickly demonstrate scalability analysis for the benchmark elasticity problem. Okay, so we use the GAMG, and this preconditioner ensures that the system is scalable with respect to the number of processes and the problem size. So not surprisingly, we can see the runtime shows an almost linear behavior with respect to the problem size. Here, we also wanted to discuss a little bit about the limitations or the bottleneck for now. It comes from the sequential package MMG. So once the level set function is updated by solving the RDE in parallel, we generate a global level set function by performing an MPI reduction on process 0. And then we have the global input mesh from the current iteration, as well as the global level set function. So then on the process 0, the MMG will start to evolve the mesh. And then after the new mesh generated, it will be decomposed again using the mesh partitioner. And then finally broadcast to the rest of the processes. So as we can see in this pie chart, currently over 90% of the time is taken to update the mesh using MMG sequential package. So we hope to solve this problem in the near future. Next, we show the several testing case regarding 3 different classical design problems. So first, we test our framework by solving the compliance, minimization of the compliance. So the governing equation is the elasticity, and we have the volume constraint for the maximum allowable material usage. Okay. So here we use a continuous adjoint method to do the sensitivity analysis. And here is the problem, adjoint problem, with the V as adjoint displacement. And then we can calculate the topological design sensitivity. Here, the lambda 1 is the Lagrange multiplier associated to the volume constraint. Here, we wanted to give you an idea about the solver's parallel efficiency. So we solved the 3 different size of problem. The smallest problem has 100,000 tetrahedral mesh, and it's performed on the MacBook Pro. And the total runtime to convergence is around half an hour. And here we can see a bird beak bionic design. This is the largest problem we have ever tried in our experience. So in this case, it contains around 2.9 million elements, and we are able to get a convergence result around 25 hours on a big machine. And also we can quickly translate the design result to the real product by using the 3D printing technology. Okay. The second design problem is to minimize the pressure drop in between the inlet and outlet. Or in other words, we minimize the power dissipation of the flow system. So for now, we assume that the fluid flow is the steady state incompressible laminar flow. So in our LSATS-based material-based method, we have to introduce a Brinkman model, this alpha U. So the alpha is the inverse permeability. So when the characteristic function chi is equal to 0, the alpha is infinite. So we stop the flow. And if chi is equal to 1, we recover the Navier-Stokes. So for computing the sensitivity, we will have to solve this adjoint problem and its corresponding adjoint boundary conditions here. This is the design sensitivities. Okay, here is a quick view of a testing example for a diesel oxidation catalyst design. We are aiming to optimize these 3 pipe connectors in white color, and the blue pipes are the fixed design domain. So this is the optimal solution for the Reynolds number of 300. Okay, so in the fluid optimization, the body-fitted mesh is very helpful when we wanted to convert the mesh representation to an editable CAD data. And also we can quickly output the connector part and the pipe part separately to the manufacturer. Then we use the CAD data to do the numerical experiment. So in this case, we use the commercial software CAD package, COMSOL Multiphysics, so we can generate a high quality boundary layer mesh as shown below. Okay, the last optimization problem we are going to show today is the multiphysics problem, fluid structure interaction. Basically, the FSI optimization problem can be classified into dry FSI and wet FSI. And as its name indicates, for the dry FSI setting, only the shape and the topology of the internal structures can be optimized. But for the wet FSI setting, the methods are able to manipulate the geometry of the fluid structure boundary. So for a benchmark, we use the weak coupling condition, which means that the fluid flow applied the force on the structure and the deformation of the structure is assumed to be sufficiently small. So here is an infill structure design for the 3D dry FSI problem. The internal structure are placed here at the upstream side where the maximum deformation is seen. And most of the material at the downstream side is removed, which is quite physically reasonable. Okay, then let's take a look at the 2D wet FSI benchmark. So once again, the body-fitted adaptive mesh allows us to separate and reunion the fluid and solid computational domains iteratively. And we can see the optimal solution is quite sensitive to the Reynolds number. So finally, we extend to a large-scale 3D problem, that is to optimize solar plate support structure, as we already shown in the video. Okay. So in this example, the fluid domain features around 500 to 528,000 elements, and the solid domain contains around 244,000 elements. And we perform the computation on a large workstation, which has 40 cores, and get an optimal solution within around 9 hours. Okay, so this is the CAD data translated from the mesh representation. And finally, we do the same thing in the post-processing stage in COMSOL Multiphysics for numerical experiment. Okay. So now I'd like to quickly summarize today's presentation. We proposed a complete product development workflow using the topology optimization technique. First, we use the reaction diffusion equation and the topological sensitivity to update the level set function. And the FreeFEM interfaced with the PETSI allows us to solve a large-scale 3D problems. And the MMG tool gives us quite nice features to make high-resolution results and also to save the computational resource, especially when solving the 3D problems. And finally, the optimal solution represented by the body-fitted mesh is easy to translate to the CAD data for manufacturing. In our future work, we will focus on the thermal fluid optimization problem. So we intend to design a passive heat sink cooled by the natural convection. This result is cited from Dr. Joel Alexanderson from Denmark. They use the density method and fixed mesh framework. So to get such a high resolution result, they have to use a supercomputer mounted with over 1,000 processes. So we will see if we are able to solve the similar problem on a standard workstation. And we will manufacture out the metal-based prototype and do the numerical experiment using the FreeFEM PETSI MMG. Okay, so this is all of my today's talk, and thanks very much for your kind attention.
So thank you for the impressive presentation. We have time for one small question because you are just in time.
Yes.
I have one small question, if I can.
Yeah, of course.
In your B-rep representation, you have only quads, or do you have also triangles and tetrahedrons?
Sorry, Pierre.
In your CAD model, do you have only quad elements, or do you have also triangles and tetrahedrons?
In a CAD model, it's how can I say, the spline representation without any element. It's only the
Okay.
yeah.
Okay. Thank you.
I had a small question. So how do you convert the mesh into spline? Like is there some software or you've written your own code for that?
We use a commercial software package, but also this algorithm is a very hot topic in the CAD industry. So we can see we can see a lot of researchers to propose such a converting algorithm in the CAD industry.
Okay, thank you.
Okay, so thank you.